Okay, so it's a great personal pleasure for me to introduce Tom Mitchell as our next speaker. Tom was born in Pennsylvania and he grew up in upstate New York. He got his bachelor's from MIT in 1973 and his PhD from Stanford in 1979, where his advisor was Bruce Buchanan. He then joined the faculty at Rutgers up the road for about 6 or 7 years. And then in '86, he moved to Carnegie Mellon, where he's been ever since. In 2000, he spent about a year or so at a startup company called Whizbang, where he was chief scientist and vice president. Since 2006, he's been the head, actually the founding head, of the machine learning department at Carnegie Mellon, which is the first machine learning department at any university in the world. He's got a long list of honors and awards, to name a few. He won the Computers and Thought Award in 1983, which goes to an outstanding young researcher in AI. He's been a fellow of the AAAI since 1990, and in 2008 he was elected fellow of the AAAS. In 2010 he became a member of the National Academy of Engineering. Tom's area of research is machine learning. He's been a leader in the field since its earliest days, co-founding both one of the main journals and one of the main conferences in the field. So his talk is on never-ending learning, a title which I think aptly describes his research style and career very well, from the earliest work on version spaces right up to his most recent work on analyzing fMRI brain images and never-ending language learning, which he's going to be talking about today. His work is always new and exciting, boldly pioneering, and an inspiration to the entire field. So please welcome Tom Mitchell.
Well, thanks, Rob, and thanks also Bob and John and the other organizers of this meeting. It's really a fascinating opportunity to get together with a unique collection of individuals. So I immediately booked the hotel for the entire period of time when I heard that I had a chance to attend. Here's an interesting quote from Alan Turing. "What we want is a machine that can learn from experience." And as with so many other things, Alan Turing saw it early, before most people, and had some insight into where computer science may go in the future. So I think it's interesting to ask, if he were here today, actually Dick Lipton is going to give a talk tomorrow on what Turing would say if he were here today, so we'll find out the truth. But let me speculate that if he were here today, it's interesting to ask, would he be pleased? Would he be disappointed with the progress we've made on this goal? And to be honest, I think he would be pleased and he would be disappointed. And that's what my talk is about. So what do we mean by learning? It's quite simple, really. We want algorithms that improve their performance at some task with some kind of experience. And we can make well-defined machine learning problems as soon as we pin down what are these three parameters of the problem. And so if we look today at the field of learning, we see there are many successes. We have many computer systems that, for example, work with structured data, structured databases like medical records, and given a collection of historical medical records, can learn which patient features predict the outcome of some treatment. We have other programs that learn not over structured data, but over sensory data, speech data. The voice recognition systems that are commercially the top ones today are all based on machine learning. In fact, they're based on a two-stage machine learning, one where you train the system in the factory by giving it microphone signals where the person says different words. So a training example to a speech recognition system would be the microphone signal, and the label elephant. That's what they were saying here. And with a collection of those kind of training examples, the system can be trained to look at future microphone signals and determine what word is being said. It's two-stage in the sense that after it's in the factory trained and you get it home, it continues, at least the best ones, continue to train to your individual voice. And so that makes it a particularly interesting example of a learning system. There are also systems to work with visual imagery data. For example, the best program you can write to recognize your mother in a photograph is a machine learning program. Even though you can recognize your mother very well, you don't know the recipe. You don't know how to write the algorithm to do it, even though you can do it. And there are many things like that, including speech recognition, recognizing your mother, extracting facts from text, where we people are very good at it, and it's very easy for us to label data, but it's very hard for us to know to articulate what is the algorithm by which a computer would do it. And that's the sweet spot for machine learning. Because if you think of the Venn diagram of all possible software, there are parts of that Venn diagram that include things like matrix multiplication, where we know the recipe, we can write it down. And then there are things like recognizing your mother in a photograph, where we don't know the recipe, but we can give labeled data. And I would submit that the subset of that Venn diagram that includes where machine learning is the method of choice for software development is actually growing pretty rapidly today. Because, for example, there are more and more sensors, more and more sensory style data to have algorithms developed to work over that kind of data. And those fall into the category where it's hard for us people to write down the recipe. So I think Alan Turing would be pleased if he could see that, in fact, there are machines that learn from provided training examples, different kinds of functions, a function that maps from images to whether your mother's in it, and so forth. He would also be pleased, I think, that we have elements of a theory of learning. And Les Valiant spoke yesterday about some of that work. In fact, Les's Turing Award is for his work on theory of machine learning. And for example, part of that theory, what would you want a theory of learning to do? Well, you'd want it to relate things like this. If we're going to train a system, what's the relationship between the number of training examples we give that system, the error rate of the hypothesis that it learns, if we're training it to recognize your mother in an image, what's the relationship between the number of training examples we provide, how errorful or accurate it is after it's trained, the complexity of hypotheses that it considers, and the probability that it'll actually succeed in outputting a program, a function with that error rate. And indeed, we now have some pretty interesting theoretical results in the area of pack learning in particular that relate those. So I think Alan Turing would be pleased at those aspects of how far things have gone. But like me, he would also be disappointed, because if we really understood how to make machines learn, it would be obvious, because we would have systems that learn continually and never stop learning, like you and I. Those systems that I just mentioned, like the one that would recognize your mother in a photograph, they're short-lived learning experiences. We collect a set of images, we label them. Here's mom, mom's not in this picture. We give that data to a program, a machine learning program. We run the program terminates, which we seem very pleased about. And then we take the learned function, and the learning stage is done. Now we use that learned function to classify images and see whether our mother's in there, and that's fine. But that's not the kind of learning you do. What do you do? When I talk to my mom, by the way, and tell her that I do machine learning, she thinks she knows what I do. And I'm a little embarrassed to tell her it's not really that. Because she watched me grow up, and she knows what learning means. Learning means, well, first Tom learned to crawl and then walk and then ride a bike and play football. And in parallel with that, he was learning to count and then add and subtract and algebra and calculus. And in parallel with that, he was learning things like playing tennis and taking physics. And that physics course that he took, he got a lot of synergy with the calculus course that he was taking. And she knows things like that. And she knows that I could not have started by taking the calculus class. That would have been stupid. First, I had to learn to count. And she knows that what learning means is it means improving in many dimensions. At least that's what it means for us humans. Learning not one function where the input is an image and the output is yes or no, is your mother there? What it means to humans to learn is that we learn many, many functions, including that one about recognize your mother, but many other things, and we learn in a staged curricular fashion that doesn't stop until we die. And also that as we learn, the stuff that we've learned so far suddenly makes it possible and easier and lower sample complexity to learn the next thing. So I think Alan Turing would be disappointed that we have not reached that milestone. And when we get to the point where we really understand how to make computers learn, obviously that's the kind of system we'll build. We won't build systems that learn for 2 minutes and then we turn them off. We'll build systems that learn for minutes and days and weeks and years and decades. In fact, we won't bother to turn them off. So that's what I'd like you to help me think through for the next 40 minutes. I want to do this by describing to you a case study of a system that we have developed that we have no intention of ever turning off. And this is an attempt to study the question of how would we build a never-ending learning computer program. And here's the case study. This particular one works on the problem of learning to read the web. So that's a challenging enough problem that we think it'll be quite some time before it's solved. The input to the system is an initial ontology that defines the categories and relations we want to learn. For example, we might say we're interested in reading about people and organizations and maybe relations too. Which person works at which organization? So that's an ontology. We'll give a handful of examples, 10 to 20 of each predicate in that ontology. If we say we're interested in organizations, we might give examples like Princeton University, Microsoft, etc. If we're interested in a relation like who works at which company, we might give Bob Sedgwick, Princeton University as a pair that satisfies that relation. We'll give the web and occasional interaction with a human, which is turning out in our system to be about 5 minutes a day because we're all busy. And then the task is simply stated. Here's the spec. We just want a system that runs forever, and each day does these two things. It gets, number one, it extracts more facts from that unstructured stuff that's out there on the web to populate this initial ontology, to find more organizations and more people and more instances of the relation person works at organization, etc. And at least as important, number two, each day it must learn to do that reading better than it could yesterday. How do we know that? You'd know it's easy. You would know it if you sent it back to the same text today that it looked at yesterday. Then we'd say it reads better if it extracts more facts today more accurately than it did yesterday. Okay? So it's easy to write down the spec of what we would like. And now the brain teaser is, well, what kind of internal architecture would you build to do this? So the system we have today has not solved this problem, but I think it's interesting enough to look at as a case study. So in our case, we input by hand about 600 predicates defining different categories and relations. The system has 500 million downloaded web pages to work from. Google has allowed us to make 100,000 queries a day against its search engine. And as I mentioned, we have about 5 minutes a day of human guidance. And the results so far, the system began in January 2010, so it's a little over 2 years old. It's been running 24 hours a day. It's running right now. It's learning right now. It's a better reader right now than it was last month. And the result so far is that it's extracted a knowledge base with about 15 million beliefs, which it's considering at different levels of confidence. And when I say that, what I mean is this kind of stuff. Here is a snippet, a fragment, of those 15 million beliefs that it has extracted from the web. For example, it believes the Maple Leafs won the Stanley Cup. And their hometown is Toronto. And Toronto has a city stadium called the Maple Leaf Gardens, as well as a city paper called Globe and Mail, etc. So each of these edges is a triple, is actually a relation instance that it has in its current knowledge base as a belief. I'm not showing you the confidences here, but these are fairly high confidence beliefs that I've plotted here. And also, in the spirit of full disclosure, I need to tell you there were other edges which were incorrect. And what I'm showing you here is a subset that's correct. But this gives you an idea of the diversity of what the system, which by the way we call NEL, Never Ending Language Learner. This gives you some snippet of the diversity of things that NEL is currently reading. So let's take a look. You can actually do this yourself online, but I'm going to go away from the URL so that everybody doesn't go there immediately and crash the system. And let's look, for example, what does it believe about coffee? This is a typical kind of example. So NEL is reading, and to it, coffee is just a noun phrase that it found on the web. In fact, found it many times on the web. And so, as I mentioned, part of NEL's job is to figure out what are instances of these different categories and relations that were in the ontology. And NEL has decided that coffee is a noun phrase that refers to an element of the category foods. Okay. So that's one thing it believes about the noun phrase. It believes also that it's an agricultural product, coffee is, that it's a food. Actually, let's look at why it believes the noun phrase coffee refers to the category food. It believes that because it found coffee in each of these phrases. It found, for example, tasting cup of coffee, or caffeine, green coffee, or coffee's antioxidants, or onions, black coffee, or delightful cup of coffee, or you get the idea. And the fact that it found this noun phrase in the context of each of these phrases, found coffee in the context of each of these, gives it overwhelming probabilistic evidence, a little bit of probabilistic evidence from the fact that it occurred in this phrase, and some other independent probabilistic evidence from the fact that coffee occurred in each of these others. But taken together, that's really overwhelming evidence that coffee is a food, in NEL's mind. And what's interesting is we never told NEL any of these phrases were relevant. This is what it's been learning for the last 2 years. Right now, NEL has hundreds of thousands of these kinds of phrases that it has discovered or learned are probabilistic evidence in favor of a noun phrase referring to one category or another. So that's how NEL reads. It's not like you and I. It's reading on a scale, we might call it macro reading. It's reading by looking at all instances, all mentions of the noun phrase coffee across hundreds of millions of documents simultaneously. Okay, what else does it believe about coffee? believes it's a beverage. And then it believes coffee plays a part in certain relations. For example, the relation agricultural product came from country is satisfied in Nell's mind by the pair coffee and Ethiopia. Also coffee in Egypt. It believes coffee is an agricultural product that contains caffeine. It believes it's an agricultural product growing in the state or province Hawaii. It believes that it's grown in which kind of landscape features? Islands, mountains, and rainforests. It believes, this is my favorite, that coffee is a beverage served with baked goods like biscuits, and brownies, and cakes, and donuts, and muffins, and pastries, and bread, and cookies, and toast, and pie. You get it, right? And each of these is a concept in Nell too. So pie, it believes, is a noun phrase that refers to a baked good. We could look at it. Okay, pie is a baked good. And as we saw, it's sometimes served with coffee or beer, or milk, or hot chocolate. Beer. Why would it think that? Let's go. Why would it think pie is served with beer? Because here are the phrases: beer and a piece of apple pie. There's a noun phrase it found on the. It found beer and pie in the context of this phrase: beer and a piece of apple pie, and beer and a mince pie, and beer and slice of pie. So apparently there are people out there who enjoy it that way. And then we could ask, what it believes about beer. Well, that's another beverage, also a food, can be made from juice. I'd call that probably an error. It believes beer decreases the risk of heart disease, and so forth. Okay, so you get the idea. Nell reads in part in this kind of macroscopic way, combining weak probabilistic evidence for many phrases, many mentions of the noun phrase, and noun phrase pairs, like beer and pie, to extract probabilistic beliefs about which noun phrases refer to which categories of concepts and which pairs refer to which relations. That's one of the ways Nell reads. We'll look at the full story in a sec. So let me get us out of here. But I encourage you to go back to this URL at your leisure and browse the knowledge base. It's continuously updated online. You can browse it, and you'll find little thumbs up and thumbs down where you can give Nell feedback about whether you agree or disagree with various assertions. By the way, you'll see, as we saw there, that some of the beliefs are in bold font. All the ones we were looking at were. Those represent roughly the 1 million most confident beliefs that Nell holds. And you'll find many more stated in grayed out font. Those are the other 14 million, and those are lower confidence. Okay. So that's what Nell does. Now let's ask, how does it do it? How would you organize the system, and what have we learned? What are the design principles here that are responsible for the system working, well, let's just say as well as it does? It's not perfect. And even in those top 1 million beliefs that it's exposing, those, in fact, are about 80 to 85% accurate. So in any random sample of 10 that you look at, you'll see 8 or 9 tend to be right. You might disagree with 1 or 2. Okay, so in fact, this is a somewhat large system at this point. But the good news is there are only 4 key ideas in the design of this system. And let's go through them. So the first one, as you might guess, if you think about what Nell's doing, what is it doing? It's learning to read the web in this sense of reading, which is for every noun phrase it can find on the web, and they're on the order of 100 million distinct ones that occur multiple times. For each of those, it's trying to figure out what it refers to and relations among those. So, and it's doing that from very little training data. Remember, we prime the system by giving it a dozen, roughly 10 to 20 examples of each category, like beverage, and each relation, like agricultural product produced in country. The rest of the data it's using is unlabeled. All those 100 million noun phrases out there, all those 500 million web pages it's looking at. So the key, the heart of the problem as a machine learning task is how do you build a system that can learn from primarily unlabeled data and a little bit of labeled. So to get started, let's consider, suppose I gave you this problem. I said, for example, I have a category in mind, and here are 4 positive training examples of noun phrases that refer to my category. Your job is to come up with an algorithm that will now use the unlabeled data on the web to find more members of that category. Then you might try what we tried at first, which is, well, just search for those noun phrases on the web and pull out the contexts in which they occur. Maybe you'll find mayor of Paris and live in Cupertino. Then you can use these phrases, search for these phrases, and pull out more noun phrases that co-occur with them. And if you do, you'll find maybe mayor of San Francisco and live in denial, for example. And you will. It's there on the web. Okay, and now you might say, okay, now I have 7 members of this category. I can now go look for more contexts and then use that to get more members of that category and so forth. So it's not a bad idea, but as you see, there's this problem of things running off the rails. If you were to iterate this for 2 years, you would not be very happy with the result. So you might say, well, Tom, that's a dumb algorithm. But I actually don't think so. I defy you to come up with a better algorithm if the only input available to you is this. So the problem with this is not the algorithm, it's the problem statement. This is not the way to set up a successful semi-supervised learning problem system. A better way, and this is good idea number 1 in NEL, is don't even try the difficult problem of learning a single classification function for noun phrases that only has to do one thing, like decide whether it's a city or a person. Instead, do what turns out to be much, much easier, which is force your system to simultaneously learn many, 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 many functions. And in NEL, this turns out to be thousands of functions, where each of these black arrows represents a different classification function. So let's look in a little bit more detail. This was pretty good. You're the first person ever to pick up on that. NP is noun phrase, obviously. You're classifying noun phrases according to whether or not they're a person, which turns out to be hard. But thank you, Dick. You're the first person. You don't know how hard I worked on this slide, and nobody has ever. Okay, all right. All right, so the key is don't even try to learn one function at a time if primarily you've got available unlabeled data. Instead, do what's much easier, which is what people do, which is learn many, 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 many things simultaneously coupled. So let's look at how that can happen. So for example, here's a function we might want to learn for classifying noun phrases according to whether or not, yes or no, they refer to a person. And if we set this up as a supervised learning problem, then obviously what we do is we tune the parameters of our function to use the features of the noun phrase, which let's say this function is using those same kind of phrases that we were looking at before. It's trying to assign weights to each of these phrases that the noun phrase occurs with to maybe build a logistic regression function or something like that to classify whether this noun phrase, given its co-occurrence frequencies with each of these, refers to a person. So if we did this in a supervised learning way where I said, here's the noun phrase, yes, President Obama, yes, that refers to a person, Princeton University now. If we did that, then I'd train my algorithm to choose the parameters of this function in a way that would just minimize the difference between the prediction of that function on a given noun phrase and the true label which I'm using person as the name of that variable for the label. So basically, I just picked the parameters that minimize the number of prediction errors of that function. Now, here's the insight. If we have mostly unlabeled data, we're not going to have much of this kind of data to sum over. And so if instead, let's say we train two functions, one of them will take the noun phrase and represent it by these phrase features. The blue function instead will ignore all those phrases. It'll just look at the character string. For example, is this noun phrase capitalized? Does it end with the three letters SKI, like Goblinsky? That's actually a pretty good indicator of whether it's a person or not. Does it contain this string? That's an indicator of whether it's a person. So the blue function will take the same noun phrase, but a different view of it, a different feature vector that happens to be uncorrelated with the features that the red function is using. And now the beauty of this is key idea number one, is that how would we train this? Well, just like before, we would choose the parameters of F1 to minimize the number of prediction errors it makes over the labeled data, and similarly for function F2. But now we get a third term that we can use, another kind of constraint. Namely, over all of those 100 million noun phrases that are unlabeled, we want these two functions to agree. We might not know whether sport jacket refers to a person or not, but whatever the case, we know that the red function given sport jacket and the blue function given sport jacket ought to agree. Either they should both say yes or both say no. If they disagree, something's wrong. And so we want to choose our parameters for F1 and F2 to minimize this combined objective, where the dominant term, if we're working with a web, the dominant term is actually this agreement constraint over all that unlabeled data. And that's the key. In fact, you can prove, we have, that if you have two functions like this that use two views of the data, let's call those x1 and x2, then you can prove that if two functions are in fact pack learnable from noisy labeled data, and x1 and x2 are conditionally independent given the label, then f1 and f2 are also pack learnable from unlabeled data, as long as you also have a weak initial predictor that gives you predictions better than random, better than chance. So this is a very powerful idea. It tells us how to turn unlabeled data, if this condition is true, into information for training functions that are going to produce labels. And is this condition true here? Well, it kind of is, right? We're asking that x1 and x2 be independent given the label. So it is true that whether you find the distribution of phrases you find with a noun phrase that does refer to a person is kind of independent of the distribution here, right? So we could say President Obama is a friend, or we could say Dick Lipton is a friend. They'd have different features here, but the same features there. So in NEL, we do this on steroids. In fact, if you have n views instead of 2, the value, the leverage you get from that unlabeled data goes up exponentially with the number of views. In NEL, we use a third view, which is involves features like this. This feature says, if you have a noun phrase, you can go to this particular web page and see if you find it in this HTML context. And if so, that's a feature. Again, that's conditionally independent of the other features, given the label. And so that idea is idea number one for how we can couple the training. There are two others I'll go through very quickly, but just to show the diversity, not only can we take different views of the same noun phrase to predict a single label, we can also, for each noun phrase, try to predict many labels, like predict whether the noun phrase refers to a person, but also whether it refers to an athlete, and also whether it refers to a team, etc. And we can tell the system in advance, in fact, this is what the ontology tells it, that athlete and person obey a certain constraint, namely that if you label a noun phrase an athlete, you must also label it a person. And mutual exclusion relates, if you label it an athlete, you better not label it a sport. Those are exclusive. And so, again, each of these black arrow functions can be trained jointly as a system with it subject to these constraints. And again, every unlabeled example lets you tune the parameters of each of those black arrow functions in a way that forces the joint assignment to become increasingly consistent. Okay, so we can put those two ideas together, which Nell does. And then we can also bring in these relational the relations that Nell is trying to learn, like, for example, athlete, given two noun phrase, does it satisfy athlete play sport? Well, there's a constraint between that, of course, and the classification of the second noun phrase. If we're going to say that a noun phrase 1 and 2 satisfy play sport, then we better also say the first noun phrase is an athlete. So when you put this all together, Nell has several thousand of these black arrowed functions that it's simultaneously trying to learn. And that's actually the key. If you only get one idea out of this talk, that's probably the most central idea in Nell that determines why you can train a system and let it run for a couple of years and it doesn't run off the rails. It's because taken together, this collection of learning problems forms a much easier, a much more constrained learning problem than if you tried to solve any one of those solely, separately. Okay, so there's good idea number one. Let's look at good idea number two. So if good idea number one is, in order to successfully train from mostly unlabeled data, you should couple the training of many functions. That leads to this obvious question. How can we get more coupling constraints? Every time we add more coupling constraints, the learning improves. Every time we learn another function, or insist that you learn another category or another extractor, performance improves. And so key idea number two is Nell learns new coupling constraints. How? Well, now that it has a knowledge base with 15 million beliefs at different levels of confidence, it can data mine that knowledge base to discover empirical regularities that hold in the world it's reading about. So here's an example. In English, this horn clause rule says, if athlete X plays for team Z and team Z plays sport Y, then athlete X plays sport Y with probability 0.93. Okay, so that makes sense to you and I. It's kind of common sense, but we never told Nell. It learned this because at this point it knows about hundreds of sports and probably thousands of teams and thousands of athletes, and there's this empirical regularity in the collection of facts it's been able to read. So key idea number two is data mine the collection of beliefs that you're reading. This will give you these kind of rules which actually increase the density of the coupling constraints that improves the sample complexity of your learning, but also allows you to infer new beliefs without reading. So if you look at the collection of beliefs Nell has, or rules that Nell has learned, has now learned thousands of these kind of rules, but you see there are things like if Team X won the Stanley Cup, then they probably play in the NHL. So a lot of mundane regularities about the world that we didn't tell the system, but that just show up once you get enough beliefs. There are also some losers. This top one, for example, is interestingly a rule that Nell learned during its first year, which would not learn now. And that rule says that if a team X plays basketball, then they play in the NBA. That's not true. However, at the time that Nell learned it, there were 35 matching basketball teams, all of whom, if it knew what league they played in, actually 35 where it knew they played basketball and played in the NBA. There were 0 negative examples, and there were 35 unknown examples where it knew that they played basketball, but it didn't yet know what league they played in. So it had no counter data, no counter evidence to that rule. Why? Well, remember how it reads? It reads in this kind of macro scale. And what is good at reading, therefore, are about noun phrases that are mentioned many times, because then it can integrate the probabilistic evidence from many sources. So it'd be good, and what's mentioned many times? Professional teams. What's mentioned rarely? My high school basketball team. And so Nell simply was better at reading things that are mentioned a lot, professional sports teams, and poor at reading things that are mentioned rarely. And so given the skewed ability to read about the world, this is in fact an empirical regularity that held in that skewed world. Now, a year and a half later, Nell has improved its ability to read, so it knows about the NCAA and lots of other leagues, and so it no longer produces this rule when you run it. Okay, so that's good idea number 2. And just to summarize how that relates to good idea number 1, here's our network of black arrow functions to be learned to classify different noun phrases or noun phrase pairs. When Nell discovers this Hornclaw's rule, that really is just precisely one more coupling constraint that in this case, that particular rule is a new constraint on the joint assignment between these 3 relations. So you see we get into this virtuous cycle, where the better you can read, the more you can populate the knowledge base to learn horn clauses like this. The more horn clauses you learn, the better you can constrain the training of these black arrow reading functions. And so as Nell continues forward, it's improving by virtue of learning those rules. That leads subsequently to improving its ability to read the instances. And that's a virtuous cycle. That's precisely the kind of thing we're targeting and trying to get into this system. Okay, so what is key idea number 3? Key idea number 3 is, well, here's an observation. Nell now knows about just about every country on Earth. It has a list of a couple hundred countries. Those of you who count carefully know there aren't that many countries. But it has them all, and it has synonyms for them, and it has some errors too. But the point is, if we run Nell for another couple of years, which we absolutely will, it's not going to find out any more countries. It's there. It's saturated, what it can learn about countries. And if you think of trying to design a true learning system that goes on forever, improving, then there's this interesting question of what do you do in terms of designing an architecture to build a system so that it won't just saturate, kind of learn up all the things that you asked it to learn and now it's done. We don't do that, you and I. So key idea number 3 is you want to keep growing this ontology of reading tasks and predicates, categories, and relations that you're learning about. So in Nell, there's a component now which does that. It adds new relations to the ontology. Here's the algorithm. It's quite simple. Namely, for each pair of categories in the ontology, let's take person and musical instrument. For each pair of categories, it's going to collect the known instances of those two, all the people that it knows about, all the musical instruments that it knows about, and it's going to co-cluster pairs of noun phrases, pairs of people and musical instruments that co-occur a lot in the same sentence, and the phrase contexts that connect them. And when it does that, for example, for musical instrument and musician, it finds, for example, here are pairs of noun phrases that occur way too often to be coincidence. Sitar and George Harrison. And furthermore, those pairs co-occur with these same text phrases, like Vibes Master Lionel Hampton. And so Nell essentially says there is some relation. Of course, formally a relation is just a set of ordered pairs, right? So here's a set of ordered pairs, typed by musical instrument and musician, and a set of extraction patterns that occur with those ordered pairs. And so Nell suggests that it should add the relation master to its ontology. How does it get master? Well, in this cluster, master happens to be the phrase that's closest to the center of the cluster. So it just picks that. In fact, the relation it will really make up is it taps on the domain and range types, so it'll call this musical instrument master musician. Okay? And similarly, if we give it the two categories cell type and chemical, it finds here are pairs that occur way too often to be coincidence, and they occur with these phrases. So it makes up the relation cell type that release chemical. And it seeds itself with these examples which it has found. Now remember when we looked at coffee? One reason I picked coffee as the example to show you is every one of those relations that coffee played a role in, like where is it grown and what is it served with, every one of those relations were discovered this way by Nell. We didn't give it any of those relations about coffee. So this mechanism actually works pretty well. It would have worked terribly the first 6 months of Nell's existence, because Nell didn't at that point know enough about the thousands of beverages and foods and chemicals and cell types and mammals and plants. But now that it does, it's not so hard for it to learn to invent these new relations. And in fact, here's a sample of recently self-added relations that Nell has discovered from that clustering process and added to its ontology. So you get things from animal eats vegetable, to food decreases risk of disease, to country has sports fans, etc. So that's good idea 3. And good idea 4 is kind of implicit in everything that I've been saying, which is if we want to try to build systems that learn a diversity of functions over forever, then key idea number 4 is do that in a staged curricular way. And in fact, here's the sequence of learning tasks that we have primarily manually constrained Nell to learn. When we started it off, it was just these first 2. We only asked it in the first 6 to 12 months to focus on learning to classify noun phrases and noun phrase pairs into those categories and relations. But once it got good at that, then it was in a position to discover those horn clause rules that we talked about. Then it was also in a position, although I didn't talk about this, to deal with the really nasty problem that noun phrases are not the same thing as the concepts they refer to. There's a many-to-many mapping. Apple could refer to a fruit or a computer. So it's also learning knowledge to decide which noun phrases are co-referent. We saw discovering relations to extend the ontology. There's some more work we're doing. But you get the point is that problems that seem hard, if you just pick one out of the middle, can become easy once the system gets to a stage of competence and a stage of having enough raw material to build on that it can do that. So, for example, discovering those relations would have been even silly to try during the first 6 months of Nell. But now that it has populated the knowledge base substantially, it's pretty a reasonable task for it to do. The red line indicates kind of where we are. There's plenty more to be done. But in the interest of time, let me wind up by saying by kind of summarizing here. So I really do think Alan Turing would be generally pleased by the progress in machine learning. But if he was serious about it, he would agree with me that we won't really demonstrate that we understand how to make computers learn until we quit doing this embarrassing thing of turning them off when they're done. Turning them off when they're done really means we don't understand how to make them learn. You don't turn me off when I'm done, right? Bad choice. But you get the idea. The fact that we train systems and then turn them off, it should be disturbing, right? It's an indication that we're not creative enough, we're not inspired enough, we're not smart enough to figure out how to organize systems that improve forever. And so I think this is one of the key next milestones for the field of computer science. And my own personal prediction is that the coming decade is going to be full of an explosion of work on never-ending intelligent agents that learn really forever. And if you take that attitude, then it's easy to see how you generate the next research subproblem to work on. You just look at your favorite learning system and you say, well, why did it plateau? Why did it stop learning? What would I have to do to modify the architecture so that it would have been able to create the next reasonable learning task to take on so that it could continue to improve? And if you're out there thinking about PhD theses, you could do this in the context of language, but you could do it in the context of robotics, if robots didn't keep breaking. You could also do it in the context of game playing. Why don't we have a never-ending chess learning program? You could do it even in that context. And the truth is, it's not that we've solved the game of chess. It's just that we have these programs that learn and then they kind of stop learning because they saturate their representational capability. Whatever it is, they saturate. They just hit a plateau. They don't keep learning until they solve the game of chess. They just get no better, and so we turn them off. And that's the part of the space we need to focus our energy on, because that's where the real advances in computer science are going to come from. Thank you.
Thank you very much. I had a question, and it is, early on you mentioned that the Nell was learning better day to day. I can certainly see how you can determine it's more consistent, but with that body of claimed beliefs and claimed knowledge, how do you know for sure it's not just more self-consistent but self-deluded? How do you know it's really more accurate?
Wow, I could not have hoped for a better question. That's an awesome question. Really, it's maybe the fundamental theoretical question at the heart of this, which is, if you think about it, an autonomous system can measure how self-consistent it is. It cannot measure how correct it is. They're two different notions. And let me just cheat. I thought of oh no, what happened to my slides? Slides, please. Lights, please.
No light.
So that really is the key challenge here. And there's plenty of, I think, really interesting work to be done on this question of what is the relationship between consistency, internal consistency, and correctness. And the reason I want to pull up this slide is here's one very simple theoretical result, which once you see it, you can kind of see directions you could run with it. Let's go back to the example that I actually mentioned in the talk, where I have two different functions that are trying to predict the same label from two different views of the noun phrase. Here's the statement that I think you could see is true. If these two functions make independent errors, and both have accuracy that's better than 0.5, then the true error rate of each of them is at worst the rate at which they disagree over unlabeled data U. So think about it this way. If I have two functions and they're making independent errors, and they agree 90% of the time, they can't possibly be only 70% correct. If they were 70% correct, they'd be disagreeing a lot more frequently than that. So there is a very interesting relation between internal consistency and accuracy under certain assumptions. And in NEL, we're trying really hard to make those assumptions hold. For example, this one assumes independent errors. Well, one way to achieve that is to have x2 and x1 be conditionally independent given the label y. But once you see, this is just a simple result. What we really want to know, and here I'd love some help, how does this relationship vary with the properties of that graph of functions that we're coupling the training of? If you think about the graph with those black arrows and all the coupling constraints, what are the properties of that network of functions and their interconstraints that determine the relationship between consistency and correctness? So that's a great question.
Tom, you're familiar with the work of Doug Leonard. He started out originally by working on some aspects of automated discovery in more narrowly constrained areas, and he built this big corpus of knowledge. So I'm wondering if you would put this work on NEL in context by comparing and contrasting it with what happened with psych.
Yeah,
I mean, assuming if they had your key issues, your key ideas in psych, would it be about the same, or would they be significantly different in some ways?
So those of you who are not aware of psych, it's an effort that Doug Leonard has led for several decades now to build a large knowledge base with the assumption that that's really what there's no way you're going to build really intelligent systems without a large knowledge base. So Doug has been organizing an effort to do that, initially very manually. So when he started in the 80s, for the first 20 years, they did that primarily manually. And I tease Doug because I tell him we're racing, and eventually I think, if we succeed, we'll just outrace psych. But there are also some drawbacks to what we're doing relative to psych. So for example, psych has a much more sophisticated knowledge representation that captures subtleties that we're not getting at here. So if you think about, for example, this knowledge graph that I showed, even though it's impressive in its size, it's pretty simple. It doesn't have the notion of, bears talk in the context of Winnie the Pooh, the story, but they don't talk in general. It doesn't have a notion of conditionals. It doesn't have, there are a lot of kinds of things we can say in language that our representation, and more importantly, NEL's ability to learn it, falls short of what psych does. So I think there's actually an interesting marriage between the two approaches that would be very profitable.
Will the never-ending aspect of PlayHub with delivering systems that meet certain specifications, and will we ever feel threatened by systems that keep learning?
Wow. It will certainly play havoc with our need to verify that our systems work well, right? Anytime you have a learning system, you have the interesting question of how do you guarantee correctness or even just bound that. The only kind of weak statement we can say right now is, based on sampling and testing with humans, NEL's knowledge base is about 80 to 85% accurate. That's a very weak kind of guarantee if you're trying to use it for something specific.
You could say you could deliver something at least as good.
Right. On average, right? Because the truth is, it's going to vary with what text you give it to look at and how difficult it is to use what it has learned for the reading to do that. So I think there is a really important question there that you're raising about the interaction between learning systems in general and this. Whether people will feel threatened, it's a great question. Honestly, I think, the easy thing for me to say is, nah, don't worry about it. But I don't think that. I think that there's a decent chance that within the next decade or so, computers will really learn to read by some kind of learning mechanism. It won't be just Nell, it'll be something more sophisticated, but research in this area is very active, and there's, I think, a decent chance that within 10 or 15 years, computers will read in the sense that we read, that they will be able to look at a sentence, understand what the author intended, and say one of three things. Either, oh yeah, I already knew that, or, gee, I didn't know that, but okay, it's consistent with what I know, so I'll believe it. Or number three, I don't believe that because I already know X, Y, and Z. And when computers get to that point, think of it this way. If you read a book a day for 100 years, how many books do you read? 36,500. If you read a book a day for 100 years, 36,500 books. Amazon has over 1 million books online right now. When computers read, they'll read it all. Why not? And they'll be better read than you and I by a factor of thousands. And they will become our reading assistants. That's what will happen if we're lucky. And I think we will. I think that's the way we'll take it. I think they will become our reading assistants. We won't have search engines in the same way that we have them today. Instead, we will have reading assistants. And the biologist who can't keep up with 5,000 articles coming out in her area each year will just have a reading assistant that will read that stuff and summarize and provide it. It'll be better than a search engine. So whether we should fear that, I don't know. I mean, I think the question of whether we should fear intelligent computers is the interesting one.
So from the examples that you showed us here,
Thanks.
from the examples, I noticed two missing components, which are time and probability. So do you think Nell can deal with facts that are probabilistic and that are timed? And whether do you think having that knowledge is just a tweak or it's conceptually different?
Yeah, I'm sorry, I was just having a hard time hearing the...
Sorry, so I noticed that the two things that are missing are time and probabilities.
Yeah, good. So I use the word confidence instead of probability because Nell does have numbers between 0 and 1 on each of these beliefs. They're not calibrated to probabilities yet, but that's very much the spirit of what it's doing. Time is a critical issue that's not addressed in the system. In fact, if you browse the knowledge base, you will find, for example, Nell believes Obama is president, Nell believes Bush is president, Nell believes Kennedy is president, and Nell knows that you can only have one president. But what's it to do? It's got overwhelming evidence for all three of those statements. And so we're working... Partha Talukdar is one of our postdocs working on the problem of temporal scoping, but you put your finger on one of the key shortcomings of the current system.
We should take a break now because we have to start up again at 3:30, so thanks for this talk.